Aloha everyone, and welcome to the Maui Institute for Astronomy. I am Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And one of the things that I get to do is put together these talks. And this month we have a very special speaker, Dr. Jeff Kuhn. Dr. Kuhn actually got his undergraduate degree at Kalamazoo Community College. Am I correct? No. Close.
It's called Kalamazoo College.
Kalamazoo College. Okay, close. Kalamazoo College. Went on to Princeton, graduated from Princeton, and has been to Sunspot, Michigan State, where I first met Jeff. And then he came out to the University of Hawaii to be the director of the Maui, the Haleakalā division of the Institute for Astronomy. Did that for a number of years, and now he's focusing more on his research, and including planets. And so, when we give him a nice Maui welcome, and thank you very much.
I don't think Kalamazoo actually has it. Can you hear me okay? Okay. So our task for today is for me to give you some of the ideas that will allow you to go home and build your own telescope to look for life in the universe. Because the truth is that none of the large telescopes that we're now building, that astronomers are building, are really designed for this, what I think is a terribly, terribly important problem. Looking for life in the universe. So let's start off by translating that question into what I think is the really important question that we all ask, which is life on Earth special? Are we in some kind of a special position such that nowhere else in the universe is there life? I don't know whether we want to call ourselves intelligent, but life that's highly developed. And I think we're very close to being able to make this not a philosophy problem, but a real science problem that we could do through the kind of tools that astronomers are used to developing and are close to having in our hands right now. Okay, so just some historical perspective on this question of are we special? We used to think we were a lot more special than we are now, right? Because if you go back, the most successful model for the cosmology that we live in is successful in the sense of it lasted the longest period of time, is the Ptolemaic picture of the universe, which put us dead center in the middle of the universe, and everything moved around us. Now, of course, it took many hundreds of years, but we know that that's not true. We decided that we're not dead center. We're a little bit off from the center of the universe, but still pretty close to the center of the universe, right? So the Copernican model said that the universe was all around us, the center of the universe was the sun, and we were just a little bit displaced from that. So we sort of evolved away from the perspective that we're not as special. In the sort of modern era of astronomy, we decided that there was a galaxy, but we still believed that our position in the galaxy was special. And so it was called the Captain was an astronomer about 150 years ago, and he had a model of the galaxy, and he said, we're still at the center of that. And of course, over your lifetime, well, some of our lifetimes, we know that we're really in a galaxy that looks more like this. And where are we? Are we in a special place? No, we're not. We're off in the outskirts of this galaxy. So over the thousands of years of civilization that we know, we've evolved from believing that we're pretty special to realizing that at least our place in the universe isn't all that special. And in fact, it's even less special than that. if you go to a big enough telescope or take a telescope, even here on Mauna Kea, this is a space telescope image, and integrate long enough, most of the specks of light that you see here are not stars, they're other galaxies, like that galaxy we just looked at. So we're even less special and less significant, okay? Look hard enough, and the universe has got more galaxies in it than it has stars in our own galaxy. Okay, so that's my perspective on our position in the universe. How about planets? So, as I was growing up, mostly in physics, I did take 3 astronomy classes. We were taught that it's hard to make planets. And so 25 years ago, we believed that there weren't any other solar systems in the universe. And it's only been within the last really 24 years that we know that when we look out in the sky, there's a great website if you want to learn more about this, where this is a plot of basically the full sky, and all of these dots are places where we know there are other solar systems. So we're certainly not special from the standpoint of being on a planet. And in fact, if you do an honest extrapolation of our ability to detect these faraway planets, it's true that there are more planets in the sky than there are stars. So when you look up and you see all the stars at night, note that around almost every one of them, there's at least one planet in a solar system like ours. Now, probably not every one of them, and maybe only half of them, but for those half of them, they probably have several planets, which means that there are more planets than stars. 25 years ago, we had no idea. All right, so that takes us to the next question. Is life special? I believe in this cosmological principle that says there's nothing at all special about us. I mean, we grow up from babes to adults believing from our parents that we're very special, and that's good, right? It's nice to have that feeling. But the reality is we're part of an ecology, and maybe even that ecology isn't special, and it's probably true that life isn't special. So that's my perspective on the problem. That's philosophical, and the point of my talk is that I think we're going to get to the place where we can answer this question, is life special, within the next decade or so. Okay, but to answer that question, it's pretty clear that we need one thing. We need to be able to look out at planets and see the light from those planets. That's our best and greatest hope to know if there's life in the universe. Now, I know that we've, as you know from the 1950s, we've looked for life by looking at radio signals, thinking that other civilizations might have had radio telescopes or broadcasting systems that leak out into space that we might be able to detect. And it may be that that succeeds, but we've had 50 years to look and it hasn't succeeded. And there are lots of reasons to believe that a civilization wouldn't advertise that fact. And in any case, it's a more general problem. So what I want to talk about is the possibility of devising instruments and systems that can find unavoidable signatures of life in our corner of the universe. Okay, so finding life requires knowing basic and advanced, we call them biomarkers, right? And the biomarkers are signals. In our branch of science, we call those, what we do, remote sensing. From a long way off, sensing the behavior far away. And light is the messenger that tells us what's going on around, in this case, exoplanets. And what we need is we need to have biomarkers. We need to have a signature that we can look for from a long distance that tells us that there's civilization. I don't want to spend a lot of time talking about the science of finding biomarkers for life. There are people here who are working very hard on it. Or Svetlana and others have spent time in our labs to try and find biomarkers that depend on polarimetry and spectroscopy, and I'll show you some examples of that, or this time-varying signal from an exoplanet that could be evidence of life. And I'll just give you a hint of what those are. So you know that that in a planet, if there are gases that can't last very long, in other words, they're introduced by life. Life is a process that we call non-equilibrium. It's something that happens despite the temperature of the environment. And the existence of some gases tell us that there's likely to be life, not necessarily intelligent life, but life. And so if you spread out the light into colors, like in a rainbow, and you look very carefully at the brightness, you get what we call a spectrum. So this is a spectrum from this is in the range that your eye can see, from the deep red to the deep blue. And there are places where molecules that are evidence of life show up as notches in the spectrum. If we could collect the light from a planet and see evidence of these molecules, we have a hint. It's not proof, but we have a hint that there's biological life on the planet, at least the kind of life that we know exists on water-bearing planets like the Earth. And of course, it's not at all an exhaustive search, because life could be completely different. The other markers that are maybe a little bit more robust than this are markers that depend on chlorophyll or carotenoids, or some of the things that we think evolved naturally to take energy from our star and turn it in, to take light from our star and turn it into chemical energy. There are molecules that do that, and they always have a sharp change in their color. And so the evidence of that color could also be considered a biomarker. Okay. So those are symbols of life, basic elementary life, perhaps. And there's a large number of people that are working on looking backwards at us to try and understand what does it really take to find evidence of life. How about civilized life or advanced life? Is there any way to find advanced life and not depend on them sending a signal that says, here I am? I mean, after all, right, we learned early on not to raise our hand in class, right? Or in the jungle not to yell and shout because we may become somebody's meal. The life in general is probably not going to naturally advertise itself, but one of the features of life, at least all the life we know, is that it requires energy, right? We actually generate a lot of energy. And how many people here have seen The Matrix, right? Remember that story? When I first saw it, I thought, it's silly to use people to make heat. Remember the scene in that movie? But it's actually, biology is a pretty efficient way of making heat because it can use all kinds of fuel. We create heat just biologically, but we also create heat every time we drive down the road, every time we use our cell phone, every time we do a Google search. Right? You know that Google places its servers in places where the cost of power is cheap, not where it's convenient to people. So the production or the use of power, if you believe that's a general feature of civilization, uses energy. And in fact, we can extrapolate our use of energy, and it's growing significantly faster than our population. It's likely that signal, the use of energy which produces heat, is a biomarker. And it's probably going to be possible to disentangle that as a marker of advanced life. Okay, so suppose we get smart and we start using energy in an intelligent way. Right? There's a problem as if we continue to use power to do our cell phones or whatever, we're going to produce heat. That is an unavoidable global warming problem, right? And in fact, we now use enough power that the heat we produce on our planet just due to that power consumption is at the same level as the fluctuations in the brightness of the sun, which is surprising. It's a lot of heat, and it's a lot of power. The only way to not produce global warming with the power that we use, this is a quiz, is what? Well, if we use the sunlight that strikes the Earth, take the energy out of the sunlight and then dump the heat back into the environment, then we're using power that would have heated the Earth anyway. And it seems quite likely that if there is an advanced civilization, that's what they're going to end up doing and what we should do, or they'll face this unavoidable global warming problem that we will face. So invest in photovoltaics. That's our future. Now, there's an astronomical signal to that. The astronomical signal is if we absorb all the sunlight that strikes the Earth, use it for our purposes, and then dump it into the planet as heat to heat the planet, what happens to the planet as you look at it from a distance? It wouldn't look like this planet here, because this planet is reflecting sunlight or starlight. It's the albedo effect, right? So when we get smart, our planet from a distance will look completely dark, except in the infrared. And it might look like this planet. It might look dark until you put on your infrared glasses, like Arnold Schwarzenegger, and you would see a glowing planet at 10 microns. Okay? That's an astronomical signal, and it's one we could look for. So that is an example of a civilization biomarker that, in fact, is possibly detectable with the instruments I'm going to tell you about now.
Question, what does albedo mean?
Albedo is the ratio. It's basically the reflectivity of the planet. So a planet which reflects a lot of its light, like the poles do where there's snow, has a high albedo. A planet which absorbs all the light has a low albedo. So in the future, if we're smart about how we use energy and we absorb all the sunlight, we'll have a very low albedo. Yeah?
What would be the subtle difference between solar photovoltaic usage and, say, a planet covered with soot?
Well,
Turn most of that sunlight into heat.
we wouldn't be able to distinguish it. So your point is this the kind of civilization biomarker which is unambiguous? And the answer is probably not. The way to get around those things is to use the geographical distribution and the rotation of the planet to separate these. Let me show you what I mean. So for example, imagine it's a civilization which is not so far advanced and isn't just using all of its starlight, but a planet like us. This is an infrared picture from a satellite of Michigan, where I'm from, and it shows already that where there's civilization, we can see an infrared glow. And it's a very significant infrared glow, and it comes from the energy consumption where the civilization is concentrated. In a planet, it's quite likely, it seems to me, that civilization will not be uniformly distributed around the planet just because of the geography of the planet and the efficiencies of doing what you do in some areas and living in other areas, for example. But this geographic distribution of heat is something that also provides us with a civilization biomarker that we may be able to use if we can build a telescope that's sensitive enough to see that. And these are infrared signals. Okay? So our hardest problem, so that's a sample of some of the markers, biomarkers for civilization and for life that are interesting and we could develop. But it's true, it's very clear that the hardest problem is to separate and to see the light from an exoplanet and distinguish it from the star that it's around. And let me try to explain to you how hard that is, but how you can go home and build something that maybe gets us there if we have enough money. Okay, so here's our let's do some physics. Here's a star, okay, and here's a planet. And the planet that we see is either glowing in the infrared, and remember, if it's glowing in the infrared, then what we're measuring really by how bright it is its temperature, or it's reflecting light from the planet. from the star, sorry. The problem we have in astronomy is that this distance compared to the distance to the star is tiny, okay? You can't go out with your binoculars and see those exoplanets and next to it see the star. They're all blended together with every telescope that we now have almost. So our problem is knowing how bright the planet is compared to the star, or somehow making the planet brighter so that when you combine all of the light, you have a chance of separating the light from the planet from the light from the star. So it's what you'd call a contrast problem, right? You want the contrast, the ratio of the brightness of the star to the brightness of the planet. You want to make that ratio the brightness of the planet divided by the brightness of the star. You want to make that ratio as big as you can make it. That's the contrast. Okay, how could we make the planet brighter? Well, the easiest thing to do, since we're seeing this in reflected light, is to make the star brighter, right? So if I make the star brighter, then the planet will be brighter. How do we make stars brighter? Turn up the wick. But my PowerPoint simulation is here to help you answer that question. How do you make, what happened to that star when it got brighter? It didn't actually get bigger, but that would make it brighter. It got bluer. See the blue? That's blue. You can make a star brighter by making it bluer. Bluer means what? Hotter, right? And that's the big difference between most of the stars in the universe, is their temperature or their color. And we can measure their temperature by measuring their color. So the other way to make the planet brighter is to do what? Yes, get closer. If we get closer, it gets brighter, right? Right? Its distance from us hasn't changed very much, but if we make it closer, it will certainly appear brighter to us, right? Because it intercepts more light from the star. And so the contrast here gets better, gets more favorable for seeing the planet, right? I can't actually force it to be closer, and if I have a better telescope, the point of this is that some planets will be closer and those will be the ones that are brighter. So it's just those that happen to satisfy that criterion. I'm going to try and get to the point to tell you how and what planets we can look for. Okay, so imagine a star which its temperature varies, so think of something like the sun, and it's a distance d away from the planet. So the brightness of the star is S, and the brightness of the planet is P. The temperature of the planet is going to be related to how much energy it gets, right? That's why the Earth has the temperature it has, because it gets a certain amount of energy from the sun. If you put it closer to the sun, we would be hotter, and we would get more energy, and of course we'd be brighter. Well, okay, so the contrast is the ratio of these. What happens if we kept the temperature of the star, of the planet, the same? Because I'm interested now in planets that might have water. Planets that might have water are planets that have about the same temperature, right? Planets that have about the same temperature are going to get about the same amount of energy from their planet, from their star, and therefore a planet which is next to a blue star that has the same temperature as this planet will be closer or further away. It's going to have to be further away, and it's going to have the same amount of energy as this one, but which of these stars is brighter? The blue one. So which of these is harder to detect in terms of the contrast? Well, the contrast is the energy you see from the planet divided by the energy that you see from the star. So around a blue star, for a planet which has about the same temperature as the Earth, the contrast will be less. It will be harder to see. And conversely, around a red star, if it has the same temperature, it'll be closer because that star is cooler, and the contrast will be bigger. So if we're interested in looking for life around planets that are kind of like the Earth, we really want to look for cooler stars, probably, than the sun. And in fact, here's a plot that shows, as of, I think, a couple months ago, it's a complicated graph, but on this axis is the temperature of the star, and on this axis is the distance of the planet away from the star, and it's measured in astronomical units. An astronomical unit is the average distance of the Earth from the sun. And so the sun has a temperature which is about here, and here's 10 to the 0 is another way of saying 1. 1 AU is right here, and so here's where the Earth is. And all the planets which have a temperature about like the Earth fall along this line. Okay? And the point of this graph is just to say that of all the extrasolar planets that we've detected, mostly from an experiment called Kepler, there are about 20 along this line, but there's nothing unusual about the Earth location. In fact, there's probably lots of planets that are like the Earth, which agrees with our developing cosmology. The Earth is not special, right? That's reassuring. Okay, so this is more complicated, but I have to come back to this later. So this shows what the contrast actually is for planets that are like the Earth as a function of the temperature of the star, and this axis shows the contrast, P over S. Okay, now there are a bunch of curves on here. The takeaway from this is that the contrast is a tiny number. Okay, 10 to the minus 6 is 1 millionth. 10 to the minus 8 is 10 billionths. The brightness of the planet compared to the brightness of the star that we want to detect is a tiny, tiny number. How can we make the number better? Well, from this graph, all these lines go up if you go to a cooler temperature star. That's what we saw in the previous graph, right? The other way that we could increase the contrast, of course, is if we increase the size of the planet, right? Because if the planet is bigger, then it will reflect more light without changing the brightness of the star, so the contrast goes up. So if you increase a planet from being something like an Earth to being 5 times the diameter of the Earth, the line will go up. Okay, the colors refer to the wavelength. Because stars have less energy in the infrared, and because the Earth begins to radiate energy in the infrared, we can increase the contrast by going to longer wavelengths. So at 5 microns, so visible light is, for reference, is about half a micron. At a wavelength of 5 microns, you're not quite at the wavelength where Arnold Schwarzenegger could see predators, but you're halfway there. At 10 microns, this is the red line, the contrast for an Earth-like planet can be a millionth, or for a big Earth, it could be even 1/10,000th. So there's a huge range in this, and the contrast problem is to our benefit in finding planets when we look for stars that are cooler and when we go into the infrared. Make sense? Okay. So this is the problem, right? So our problem is to look into the headlights and see count the hairs on the head of the driver against the glare of those headlights. And the headlights are between 1/10,000th and 1/10 billionth, or the headlights are 10,000 or 10 billion times brighter than the light that we're going to get from the feature that we want to see nearby. That's our contrast problem. And what we say is this is a scattered light problem. So, right, if you had a perfect optical system where all the light from the headlight only appeared in the image of the headlight, then you wouldn't have this glare, right? I mean, it's like your windshield. If your windshield was completely clean, you'd never have to worry about glare from the oncoming drivers. You'd simply look away from that light and it wouldn't distract you. The problem in optics is light goes where it's not wanted. So a tiny fraction of the light from the headlights ends up in our image on top of the thing that we want to see. That's called scattered light. Okay, so here's a picture of a ground telescope picture of the sky. This is the Milky Way, so it's a big piece of the sky. Each one of those is a star. You look at that and you now say, oh, but there are more planets buried in that image than there are stars. And our task is to unbury the planet. So if you blow up a stellar image, say there, this is what you actually see in a telescope. It's horrible, right? I mean, the star is, we couldn't really see in this image. All of this is scattered light. It's glare in our conventional telescope, in our optics. There is a planet buried in there, and you can't see it, but I'll color it so you can.
In the scale that you're using there, if there was no scattered light, would the star even be a pixel on the screen?
No. If there was no scattered light, the star is infinitesimally small, and of course we never achieve that. So real optics always make things appear with a certain size. So any real telescope optics, any one of the extrasolar planets I'm going to show you from a catalog in a minute is going to appear in the midst of all of this scattered light, and it will be 10,000 times to 10 billion times fainter than the light that we're looking at. That's the problem we've got to deal with. It kind of seems hopeless, doesn't it? But it's not. It's not hopeless. So there are lots of reasons why telescopes do bad things to light. They put it in the wrong place. This is an image that shows, I mean, you may have looked at telescope images and said, do all stars have crosses around them? Right? Is it true that stars, so this image is too blown out to see, but you can start to see there's a little bit of a cross in there. You might have thought that all stars have little crosses in them because most of the pictures that we have from telescopes show crosses of one form or another. They don't, it turns out. That's from our telescopes. You might say, well, what if we go to the biggest and the baddest telescope on the Earth? Does that solve the problem for us so we can see extrasolar planets? The biggest and the baddest telescope on the Earth is right over on Hawaii, in Mauna Kea. The world's largest telescope is Keck. There's Keck. Can it see extrasolar planets? What does it do to light from a star? Well, this is what the Keck mirror is really like when you look at what it does to a wavefront. It does damage. A wavefront should be perfectly uniform. And in fact, in the Keck telescope, you get to see every individual mirror segment. And I think I skipped an image. I skipped that one. The first thing you got to do to be able to see the image I'm going to show you in the next slide is you have to correct for the scattering that the atmosphere does. Right? And so this is some real adaptive optics that was done here in Hawaii. So this is what the atmosphere does.
Right now is seeing.
This is Buzz Graves, who built one of the first adaptive optic systems used for a telescope. This is 15 years ago. So light should have been a point, less than a single pixel, and it looks like that. Yes. So this is a star. This is what you see. This is what the atmosphere does to us. It's a terrible thing. But now when you turn on the adaptive optics, that's what we get. That's not bad. You see how the light is all concentrated. It's still not a single pixel. But the first thing we have to do to be able to solve the problem of seeing exoplanets is we have to fix the atmosphere. It's doing it by, so what the atmosphere does is so think about waves coming in off the ocean. Light is the same way, it's waves. Waves coming in off the ocean should be a perfectly straight line when they come to the shore. The effects of inhomogeneities in the ocean cause the waves to break differently. The depth of the ocean does that, for example. The speed of the wave changes. the waves of light do the same thing. If you built a mirror that inverted that deformation of the wave, then when that wave reflected off of the mirror, you could undo the effects of the atmosphere. And that's what adaptive optics does. It measures how the wave is distorted by the atmosphere, and then it undoes it by reflecting the light back up to another set of optics. Yeah.
Where could we find the algorithm for that?
Ask me after class. There are lots of algorithms to do that, and there are many experts in the room who probably could answer that better than I, but we could find it on the web. Okay, all right. So once you correct that, even on the world's largest telescope, we're left with an image of a star that looks like this. That's the Keck, we call it the point spread function. That's what a star looks like on the Keck telescope, the biggest and the baddest telescope that mankind has. That's not very good. Imagine looking in there for that extrasolar planet 1 million or 10 million times fainter, and you don't have a chance. And that's because the Keck telescope has a whole bunch of these mirror segments. And what we're looking at here is an effect which is called diffraction. Okay. So if you go to space, we're still stuck with diffraction. This is a space telescope image. Okay, and there isn't any atmosphere around each one of those stars, but there are crosses on them. And that's due to what's called diffraction in our telescope. And we have to solve that problem if we're going to see extrasolar planets. Okay, it's time for an experiment. We're going to do a diffraction experiment here, each one of you. I need to turn that light off, and if you guys want to come in here to do the diffraction experiment, that's okay. So that's a bright light. Hold your thumb up and block the bright light. And block the bright light and tell me what you see. Do you see that the edge of your thumb, even though you're blocking the bright light, has a bright line around it? Okay, that's not due to hairs on your thumb. Okay, that's diffraction. Even though you block the light, it's like a wave. It sneaks around. It's like, right, sound travels in a straight line, but if I stand behind a tree and you can't see me, you're still going to be able to hear me. Okay, sound is a wave. Light is also a wave. Any sharp edge, the sharp edge of your thumb, will cause the light to sneak around, and that light is what you're seeing, that bright light. That bright light can be millions of times brighter than that extrasolar planet around these stars. Okay, that's what we have to solve. Turn that on again. Okay, so that's diffraction. Here's our stellar image. If we could eliminate the atmosphere, it would look like this. It still has a halo, it's smaller. That halo is due to the roughness of the mirror, and it still has these lines right here. What are those from? Why is there a cross? There are in almost every telescope, there's a mirror that sits above the primary mirror, and it has an edge to it, and then it has a couple of rods that hold it above the primary mirror. And you think those rods would produce a shadow? They don't produce a shadow. So, in fact, the horizontal rods produce one of these spikes. Is it the horizontal spike? It's actually the vertical spike. The scattered light is always perpendicular to the vertical direction of the edge. So this thing that we see, the spikes on stars, is due to our telescopes. Our telescopes do that. And it's a really bad thing because it lets light sneak around into our image and obstruct the Earth-like planet with aliens that's hiding in that space. So if you could get rid of that structure, then you get to see the planet that I had hiding in there. So a perfectly symmetric round aperture, that's the mirror that collects the light, would give us this, all the light would be concentrated. There's some rings, but that concentration is much nicer than what we saw with diffraction, and you can begin to see the planet. We actually have to do a little bit better. This planet is only about 1,000 times fainter than the light of the star. We have to go many orders of magnitude fainter. How do we do better? We concentrate the light even more, and the way that we do that is we make the ratio of the wavelength of our observations to the diameter of our mirror smaller. How do we do that? We go to a bigger telescope. We make D is the diameter of the telescope, or we go to shorter wavelengths. But we can make and see, we can resolve stars, planets, the star from the planet, if we go to shorter wavelengths. That's not good, right? Because we just said that the best way to see planets for their contrast is if we go to longer wavelengths. But the best way to see them separated from the glare of the stars is if we go to shorter wavelengths. So there's obviously a sweet spot in between, or we have to combine all of these things together. That's our problem. Okay, so seeing a planet requires removing the scattered light, which is caused by the atmosphere, and we get rid of that using adaptive optics. And the diffraction and the scattering effects we can start to improve by somehow removing all of the optics in front of the mirror and getting rid of any sharp edges, like your thumb that produces the scattered light. And how do we do that? Well, you tell me. Is this a good telescope for detecting extrasolar planets? Or that? Oh, that's the best one of these. They all have roughly the same area, so they collect as many photons. This one has less sharp edges in it. In fact, this minimizes the sharp edges. A round aperture. It doesn't have the support structure for the secondary, or doesn't have all of the gaps between each of the little tiny mirrors. That's what we need. How can we make a telescope that doesn't have anything in front of it? Well, the answer is we make a telescope called, let's see, so I call this an off-axis telescope. Stan likes to call it an eccentric pupil telescope, but basically it's just a telescope that brings all the light into a mirror which is not symmetric anymore, and then shuffles it off to the side where we would have the secondary mirror that then allows us to magnify and focus it. And it's only been in recent years that we've started to build telescopes like this, but this is the answer. This is what we have to do if we want to start looking for extrasolar planets. You're right. You're right. But he had other problems. Yeah, I was going to say that. One of the first ones that we've used for astronomy is one up on Haleakalā called Solar C. There's nothing to obstruct the light that comes down in here, and then it goes off to the side and back down. This is a telescope designed for looking at the atmosphere of the sun. Obviously a problem where you don't want scattered light, right? The sun is very bright. If you want to look off the edge of the sun to see faint things, then you need a telescope like this. Too small. It's just a half a meter. It's a half meter aperture. Yeah.
Does it work really well?
It works perfectly. Because I made it. No, it has many problems. It was built as a research instrument, and so the problem it has right now, it was built with 15-year-old technology, and the graduate student who is using it today is struggling to get Windows 98 to work with some of the hardware that is no longer available. Yes, yes. We did use it for that. We had a group that was using it to try and, I mean, its scattered light properties weren't particularly advantageous for that, but it does get used. Yeah. There's no theoretical maximum. You can make them in principle as big as you want, and that is one of the nice things that we use to get to our future. There's a much bigger off-axis telescope that if you go up to the summit of Haleakalā you can see. It's called the Daniel K. Inouye Solar Telescope. It's built using the same optical concept. It's a segment. This is actually a parabola. It's a segment of a parabola. All the light is sent off to the side, and then it comes down to a focus down here. And so we're catching on. That whole telescope looks like this, and if you go up there, it's really impressive. It's built up to about this level right now. They're starting to add this structure, and they will start doing the dome right now. It's impressive. You should go up if you have an opportunity. This is mankind's most expensive ground-based telescope so far. Right? It's very complex, it's very elaborate, it's very expensive. In part because of the off-axis optics, but also in part because there's an enormous amount of energy coming from the sun that we don't want. How much what?
Money.
Oh, how much money? I thought you were asking how much time will it take me to finish this? It's $340 million.
How much of that goes to you?
I wish. I wish. I would be a rich man. Essentially zero. Yes, yes. I'm sorry, what?
And with this particular telescope, when it's in operation, are we going to be able to see things?
Well, this telescope is being designed to look at the sun, and they have told us that no, you can't use it for other things because we need it. We know that because it's so absolutely unique, once it gets operating, there's an irresistible force that will use it to look for extrasolar planet problems. Yeah, yeah. Turns out you can't see the sun at night. So here's the landscape of planet or telescopes you might have heard about. They all are what we call obstructive telescopes. They have, and this is not, of course, the right picture because there's also what we call a spider that supports the secondary mirror. All of these edges produce scattered light, which is bad. These are the modern telescopes into the future, something called the 30-meter telescope project and the European Extremely Large Telescope. We will not detect extrasolar planets with these telescopes. Think of the Keck image that I showed you, and now make it 100 times worse. That's what these telescopes are. Okay. And in fact, as I said, we're starting to catch on. The Palomar telescope has been converted, downsized, into an unobstructed telescope. How would you do that? Well, the Palomar telescope has we say a pupil. If you look down it, this is 200 inches across, and then it has a big secondary, and then it has a spider that supports the secondary. How do you make it an unobstructed telescope? Well, you put a big piece of felt over the primary that blocks all the light except for this region right here, and all of a sudden it's an off-axis telescope. Okay, and a significant fraction of the venerable Hale 200-inch telescope is now being used in its mode where it's now a 1.5 meter telescope to decrease the scattered light to be able to look for extrasolar planets. So we can supplement this landscape with, there's Solar C, the telescope I showed you. There's a telescope at Big Bear Observatory called the New Solar Telescope, which now is also off-axis, unobstructed. The Hale off-axis telescope, these are solar telescopes, is being used at night. And planets, which I want to get to, is what we're building here, is a nighttime version, the world's largest off-axis telescope for nighttime use. And here's DKIST right here. Well, that's an acronym, actually.
How big do they need to be, or am I jumping ahead?
You're jumping ahead. I'll get to that. Ask me in a minute. So PLANETS is in fact an acronym that stands for Polarized Light from the Atmospheres of Nearby Extraterrestrial Systems. Well, we had to work hard to get that, and it was started by our colleagues from Toku University. I don't know, show here, shows here. So the Japanese said, look, we want to look at exo-atmospheres of nearby planets, which also are terribly faint. So we're really interested in something that allows us to do that. Turns out Mercury has an atmosphere. It's transient and it's very weak, but to study it, you need something that doesn't scatter the light. So Tohoku, the University of Hawaii, Kiepenheuer Institute, our friends from Germany are contributing partners to this. A private individual, Casey Harlington, from the Searchlight Observatory, and we think the Brazilians are going to join it. So there are a bunch of people that are interested and feeling like this is the way to the future. The mirror for planets is terribly thin, one of the thinnest ever. It's less than 5 centimeters near the center. This is a picture of the mirror as it's being tested a while ago in Rochester, New York. We'd like to push new technologies to allow us to make even bigger off-axis mirrors into the future, and so the planet's mirror is doing that. The fact that it's a relatively thin mirror is one of those technologies that that telescope is expanding on. And these are just some, this is a kind of telescope that won't work unless you're running a Windows 98 will not run this telescope. It requires a computer to actually produce the surface figure on the mirror. And in fact, the mechanism that does that is we think some really cool, they're called force actuators on the back of the mirror, with a higher density and a greater precision than anything that's been done before. So this is a technology that we want to export to even larger mirrors. Here it is. So come up and play with it. This is not actually it, but it's a 3D printed model of it, which shows that because it's off axis, it looks kind of weird. Okay, the light comes in here and comes off to the side and then goes down, and it rotates along an axis which it points to the North Pole. All right, I don't know, Stefan, I can lift it, but I might drop it. Luckily, it's not a good mirror. Okay, there it is. It is an example of what I think modern telescopes should look like, and in fact, if you look at the design of ATST that I showed you, if you remember it, it looks a lot like this. Okay, so this is real. It's this era of building telescopes where you mate information technology to very thin mirrors, and you don't make them heavy and massive to make them stiff. You make them stiff with information technology and electronics.
Jeff?
Yes?
Are there any disadvantages to this type of mirror, and why haven't there been any other telescopes made?
Well, we're all moving in that direction. Stan's comment was they're difficult to make, but in some ways they're easier to make, because now I don't have to worry about the polish on the large scale. So I can now polish mirrors in different ways, and it's possible to push. So what makes telescopes expensive is their mass. If we can make them less massive, we can make them bigger. And of course, the punchline to all of this is our future is to make very large telescopes with mirrors that are very much less massive. And this is the precursor and the test of that technology. Why it hasn't been done so much in the past is because, for one thing, astronomers are incredibly conservative. No, this is a fundamental, it's like the second law of thermodynamics, right? The astronomical community is very, very conservative. And the world's largest telescopes, starting with the Hale 100-inch to the Palomar 200-inch to the Keck telescope, they weren't built by astronomers. They were built by daring engineers, and in some cases, solar physicists. We've started to do things in committees of hundreds and thousands of people where the telescope has to do everything. And for this problem, that's not the answer. Don't get me started. Okay, so the first step in solving our problem is to make it unobstructed, to really cure diffraction. But it doesn't cure all of the diffraction, right? Because you still have the edge of the mirror on the outside. And as you know, when you put your thumb up there, there was a lot of bright light around the edge of your thumb. And the same thing is true in that circular edge of a mirror. How could we fix that? Well, we can fix it by building what's called a coronagraph. So imagine, again, that experiment where you held your thumb up, you saw the bright edge. If you had put another mask that blocked the light from that bright edge, and then some more optics to re-image, you could eliminate a lot of that scattered light. That's, never mind this complicated figure, that's what a coronagraph is. It puts additional optics to block the light from the edge of your thumb so it doesn't get mixed up with the light of the exoplanet in your final image. And the really cool thing about a coronagraph, so this is, it's a complicated graph, but it's not that bad. So if you take, If you take a slice through the brightness of an image, like what I called the PSF, so the brightness at the core of the image is here, and then it gets fainter out here. Here's a scale that goes from 1 to 1/10 billionth. Okay? A coronagraph allows you to make the light drop by 10,000 times when you get out to, remember that number lambda over d? Remember how as lambda over d got smaller, you made the core of the image smaller. Well, so a coronagraph is naturally, its performance is naturally measured in units of lambda over d. By the time you get to 5 lambda over d, a coronagraph can be 10 to the minus 5, 1/10,000th, as bright as the core of the image. So a star with a coronagraph and a good telescope will improve this by more, by probably a factor of 3. We can probably get this number down to 10 to the minus 6 on the planet's telescope at 5 lambda over d. So what does that mean, 5? It means that we can improve our scattered light, make it less, by going to shorter wavelengths, by using a coronagraph, and by using that unobstructed aperture. So what do we have to get to see a habitable zone, in other words, a planet that has water at a temperature of 300 Kelvin? Well, so the sun's brightness is here. If we were looking in the visible, the Earth would be a billion times fainter than the star. Well, at 6 lambda over d, we're not gonna make that. All of these numbers are in the regime of a 10,000th to roughly a 10 millionth for stars, host stars that are redder. That means cooler than the sun. What does that mean? It means we can achieve, with planets and a coronagraph, we can see something 1,000,000 times fainter at 5 lambda over d from the star. So as long as we're further away than 5 lambda over d from the star, we can see something 1,000,000 times fainter. What does that mean? Okay, so in the visible, 5 lambda over d means 0.25 arc seconds. What is 2.25 arc seconds? It means at a distance, a planet which is more than 4 astronomical units from the star, if it is no further than 65 light years away from us, we'll be able to see it. So this is for a star. This is independent of the star. This just says, with our coronagraph, working like the one I showed you in the previous figure, we would be able to see something which is 1,000,000 times fainter than the star, 0.25 arc seconds from the star. Now you can ask, well, is that good enough to see a planet? And it's only good enough to see the planet if the star is very red. That, I think, is the answer to your question. At longer wavelengths, this is a bigger number, and in order to see a planet at that brightness, we'd have to be 40 AU. That's out near Neptune to be able to see it. And at 10 microns, we'd have to be 5 arc seconds away, which is twice that, 80 astronomical units away from the star. What does all that mean? Well, okay. So now let's take all of the known exoplanets around bright stars and ask how many, with our planet's telescope, will we be able to see habitable zone planets around? And guess what the answer is? It's 0. None of these are habitable zone planets. Planets will not be able to see habitable zone planets because they're just too faint, even around the reddest star. So what these lines are, so this is a list that shows the distance of the planet away from the star. This is, in astronomers' terms, the brightness of the star, and the bigger the number, the fainter the star. In astronomers' terms, this is related to the temperature of the star. So which of these stars is most favorable for having a planet with the highest contrast? Well, it's the ones that have an M or a K or an M. M means cooler. G is like the sun. So at 10 microns, we'll be able to, with planets, resolve these objects if they're bright enough. We don't know if they're bright enough. similarly here. But we know that if they're habitable zone planets, we won't be able to resolve them. So why are we doing planets? Well, the answer, this is just the continuation of that list. Planets will not have the sensitivity to see habitable zone exoplanets, but it will do this. It will enable studies of cooler, more distant, right? It will see the more distant exoplanets in this list around, and that means the planets are cooler, and we'll be able to see their atmospheres, although they're not likely to have life like on Earth. The thing that is really exciting to me is that with this telescope, we get to develop and test both the biomarker signals, and we get to measure visible and infrared light from a handful of exoplanets. We will, for the first time, systematically look at the light from the atmospheres of some collection of exoplanets, even though they're not habitable zone, which allows us to enable, it enables us to test and refine the technologies needed for the next generation of world's largest telescopes that will have the sensitivity to detect life in the universe. So this is our setup. This is our enabling technology for algorithms and the physical algorithms and the physical technologies that go into a telescope that we call Colossus, which looks like that. And I've given a talk on this, so I won't say much about it, except to say, as a summary of what I hope you've learned today, that planned astronomical telescopes are not likely to find exolife. Planets is a pathfinder for the technologies and the biomarker techniques. So we got two problems there, right? One is to develop the signals that we know tell us there's life on the planet. And we also have to, for example, figure out how to support the mirror and make it lighter weight. And planets is the first step in doing that. The Colossus Telescope, which is, each one of these is 8 meters across. So this is a structure which is about the size of a football field, which has never been done before. We think that we can do it, taking these steps along the way. And this thing will ultimately allow us to study alien life in a 60 light year radius around the Earth. So there's a Planet's website if you want to learn more. There's a big Colossus website that has lots of literature and some other talks that describe what it's all about and what we're trying to do with that. Okay. Garrett, I'm done. This is the end of the talk. Okay.
Remember to repeat the questions.
Right. Okay. So Garrett.
Jeff, can you attack the contrast problem by getting a thumb that's closer to the source? So just if you use some object or even an astronomical body like one of the moons of Jupiter to block out the sun at a far enough distance to get less diffraction, and therefore you might still be able to resolve a planet off the edge?
Yes. The answer is yes. NASA is developing what they call the star shade technology, where they go out into, the question that was asked was, could we generalize the thumb concept to look for extrasolar planets by being able to move our thumb in space around stars? And that's exactly what the Starshade project is about. It's to erect in space, very distant from the detector, screen, and put a star behind the screen, and then look close to that screen for evidence of an extrasolar planet. But it has to be very far away, which is why it has to be in space and it has to be out of the atmosphere. Now, that makes it hard to study many of these systems, right? Because every time you want to look at a different star, you gotta move in space, and it's right a fraction of an astronomical unit away. Move that screen around, right, while you keep your detector where it is. But it is certainly a viable technique for doing this.
What about using something like one of the existing solar system bodies, like one of the moons of Jupiter?
Well, yeah, but then you gotta,
Then
God isn't very helpful. Yeah.
So I'm going to ask, I'll go with the obvious question. It's very clear in the early part of the book about how the off-center telescopes had to have one large mirrors.
Right.
So how are you solving that problem?
Okay, so the question was, how is it that when we go to these bigger and bigger telescopes, we're going to solve the problem of diffraction when we have actually ended up with lots of mirrors? Well, okay, so here's the problem. When we go to 60 meters across, there ain't no way we're going to get a piece of glass which is 60, 70 meters across. The best thing that we can do is to make each one of our mirrors as big as we can possibly make it. So rather than, as in the EELT or the other astronomical telescopes with mirrors that are about this big, we make these mirrors as big as we can make them. And it turns out to be about 8 meters across before you worry about other problems. The answer is that it's a compromise. And there still is a diffraction problem, but when you make the mirrors that big, we can build a coronagraph around each one of the subapertures. So we effectively minimize the scatter by building a coronagraph around each one of the subapertures. And there's some other things that have to go into this to make it work when it's that big, but the scattered light ends up being not the primary limitation. But the strategy, of course, as you point out, is to make the ratio of the area to the perimeter in your optics as large as you can make it. Is that satisfying? Okay. Yes?
Does it particularly help that each of the individual mirrors is circular as opposed to some other shape in this type of, in a telescope like this?
So the question was, is there any magic or great advantage to making each of the constituent mirrors circular? And the answer is yes. A circle maximizes the area to perimeter ratio. We don't particularly care. The gaps in the mirrors for us are not very important because we have other algorithms for putting the wavefronts together to make a real image. For us, it's the diffraction that's a harder problem, and that, again, is minimized by making it circular. No, the most difficult problem is getting the money. This is a telescope. This is a telescope which about $1 million has gone into studying a design to make it work. And that's from primarily private sources. The total cost of building this, and the study had some reputable people in it. For example, the company that built the Keck telescope and the Subaru telescope, current world's largest telescopes, was deeply involved in that study. The director of the NASA Ames Research Center is on the board for this. Joe Janai has advised us in this board. So really reputable people involved in helping us understand costs. The cost of building this, the way that the Colossus Consortium would do it, probably makes that cost about $800 million. The TMT cost, right, is already $1.3 billion. The extremely large telescope, the European version of the TMT, is probably a $2.5 billion telescope. But they're expensive because they're designed in a very different way, and they're designed to solve many, many other astronomical problems. Yes? Okay, so the question was, doesn't the Drake equation give us the expectation that the most likely distance that life will be found from us is about 150 light years away? So that's based on some understanding or some assumptions about the density of life, and there's a string of parameters that go into that. I don't really think we know enough to be able to estimate that. Within 60 light years, this telescope will be able to do a cosmic census of many hundreds of stars. And we believe that probably a quarter of those stars have a habitable zone planet around them, based on the statistical estimates from Kepler. And if a quarter of those planets, of those stars, let's say there's 600 that Colossus would look at, so there's at least 150 that may be very Earth-like. Suppose you looked out and you could see 150 planets that were like the Earth, and not a single one of them had life on it. What would you conclude? That'd be maybe. That's a very pessimistic scenario, and I think we probably learned something from that. Yeah, I frankly think that's highly unlikely. But it's this idea that we can begin to think about doing a life census for our corner of the universe, and I think we're close to being able to do that. Yes?
Are the mirrors being produced yet? Or do you think
So we have a very active research program to be able to make mirrors like this out of window glass, where the idea is to, through some cleverness, roughly shape them to be parabolic or part of a parabola, and then use information technology, 3D printing techniques, a density of actuators that you couldn't do manually by hand, to be able to electronically manifest the shape to make them good imaging systems. And why do we do that? We do that because we could take a mirror in the old style. The Subaru mirror is an 8-meter mirror, and we could decrease the mass of that mirror by a factor of 10. So rather than make it stiff by having lots of glass, we make it stiff by using electronic means. The cost is that we now have to have a lot of electronic processing power, but that's cheap. That's very cheap. Yes? To make that work. That's a good. So the question was, with a space-based diffraction mass, how long would it take to actually be able to get a signal from an extrasolar planet? And the answer is, you still need a big telescope, because you need to collect enough photons from an object that is fairly faint. But these planets that we're talking about are not faint compared to the very distant galaxies that we look at. So the size of the telescope that you would need to be able to collect enough light from a mask in space that blocks out the star but still allows the light from the planet would be something like a 4-meter telescope. Something like the JWST telescope is certainly big enough to do that, and exposures that are no more than I'm pulling this off my head, but I think a number like an hour or two would be adequate to collect enough photons from the extrasolar planet. There, the point, of course, is that you have very little noise because you've blocked the diffraction effects and the direct light from the very much brighter star. Yes? It's a really tricky problem. You're right. Sorry, the question was, how do you do that given that everything has to be orbiting the sun and it's all moving? And the answer is that you have to build a system which is active. It's going to have lasers which actively guide either the screen or the receiver, such that to a tiny fraction of, remember we talked about arc seconds here, to a tiny fraction of an arc second, that screen is maintained with the same orientation, the same separation with respect to the distant star. It's a hard problem, but it's the kind of problem NASA likes, orbital dynamics. Yes? Yes. So the question was, are these planets just reflecting light, or are they giving off light? And I kind of glossed over that, but they're doing both, right? So a lot of the light that we see from a planet is reflected from its star, right? And that's determined by how far away it is. But the other part of the light at 10 microns is determined by its temperature more than what it reflects. But it's a combination of those two effects in the infrared. So it's both the reflection of the infrared light from the star off the planet, plus the planet's own emission. Because it's so much colder than the star, we as a planet, or people, radiate in the infrared, and the star radiates mostly in the visible. Okay.
Do we have any really good techniques for picking up non-intelligent light, unadvanced light?
Ask that again.
Do we have any really good techniques for detecting unadvanced life?
Unadvanced life. You mean like
Stuff that doesn't have technology.
animals and plants? The question was, do we have good biomarkers, if I could paraphrase, do we have good biomarkers for life which is not intelligent or advanced? So scum and the oceans and that those life signals, people are still looking for the biomarkers. Some of them involve the fact that biological molecules have we say a chirality, they have a handedness, and so reflected light off of biologically active molecules can have a polarization. So that polarization may be a signal for life. If we can make a spectrum and measure the color very accurately, maybe you've heard of the controversy that there was or there is life on Mars by looking at methane. We could detect methane in a planet's atmosphere from the spectrum by looking at where certain colors of light don't exist or do exist. And methane is a potential biomarker because it doesn't last very long in the environment of space. We say it's a non-equilibrium gas. And so that's also a way of potentially finding evidence of biomarkers. It's a really hard problem, right? Because we have a bias as to what we think life should look like. And it may very well be that our ecology is very common in the universe, or it could be that it's not, in which case we're barking up the wrong tree. Yes, so the question was, for intelligent life, is it also true that we have a bias? I'm actually less pessimistic there because the laws of physics do exist, I think, over the universe, hardly changed. And the first law of thermodynamics says if you use energy, you produce heat. And so this idea of looking for a heat signal in a rotating planet, and if you go to our website, you can learn more about how that would work, is kind of universal. It doesn't really care what the civilization is doing, but just that it's using energy.
So is your actual question, you mentioned the website?
It's here. Oh, for the planets. What's the planets website? It's an IFA website. I'll email it to you. Yeah, I didn't tell you. That's sneaky, isn't it? I'll tell you. I'll put it up. It's a very old website, and we're in the process of renovating it, which is why my colleagues are pointing at me. Yeah, maybe. Okay. Yes, sir.
A question about the Colossus again, because I keep looking at that thing and I was really surprised not to see one very large mirror. You're concerned because you say you're 9 meters wide, but if you're not concerned about imperfections, if you can fix them with digital technology, why would you care? Would you not build a perfect 50-meter mirror, 100-meter mirror, and then just test it and correct it visually?
Yeah. Okay, so the question was, why have we limited ourselves to 8-meter mirrors when perfect 8-meter mirrors? Well, these aren't perfect, right? These are as imperfect as your window glass. Why don't we make mirrors that are a single face sheet that's this large? And the answer is that maybe you're right. Maybe that is a good solution, but nobody we've talked to believes that we can make 4 millimeter, maybe 1 centimeter thick glass that has that size. It turns out that architectural glass, this is all about money, right? It's about cost. Architectural glass is something that we can get as large as 8 meters. It is amazing. And if we can do that, if we can get glass that large, then we never polish this glass, by the way. So once we get what's called fire polished float glass, it never gets ground. It gets shaped by a process called deterministic slumping, and then it gets finally shaped with a process involving 3D printing on the back. So your comment is a good one, and maybe we should explore how to push technology to get bigger and bigger pieces of glass, but what we know is 8 meters is doable. Yes, Garrett.
What if you just take something like a big pool of mercury and spin it in a gravel?
And put a black hole behind it so you can keep gravity in the right direction? For a theorist, that's a great solution. We would be able to point at one star at a time with 0 integration time, but yeah, there is such a telescope that's there's one in Canada in Vancouver, which is it's roughly a 4-meter telescope, and it looks only at the zenith, and it observes stars briefly as they pass directly overhead, and it's a spinning dish with mercury. Ian.
I was just going to mention, if you're worried about big window glass, the Apple headquarters is supposedly building the largest glass manufacturing because they needed the biggest windows possible. So you might have the world's largest glass.
So the comment was, could we collaborate with Apple to build the Apple Colossus Telescope? I think that's a wonderful idea. Maybe on that. Yeah. Maybe on that note, I should let you all go. Come up and see our planets telescope, and thanks everyone for coming.